So we're going to talk about electrical basics today. We're going to start off with definitions. And the first one is going to be conductors. All right, conductors is going to be anything that's going to allow electricity to flow. So basically any type of metals, any dirty water, human beings, we're all conductors. All right, the most common conductors we're going to see in residential construction is going to be the wiring that we use. It's also going to be plumbing pipes as well, because when we talk about grounding and why we ground and how we ground, excuse me, that's all going to come into play there. So the most common ones we're going to run into in residential electric is going to be copper, pretty much. Other ones that we will see doing an inspection is going to be the aluminum, and then sometimes we'll run into some tin as well. All right. I'd like to address a little bit about these. So aluminum and tin, a lot of people get confused between the two of them. Now they're both going to be silverish in color when it comes to, looking at the actual metal portion of it. Aluminum will be a little bit shinier and newer, and I know I have a picture of it here when we get later on into the slides. But the biggest detail and the easiest way to tell the difference is going to be that aluminum is always going to have the plastic insulation. When we're dealing with branch circuit wiring, I'm not aware of any aluminum wire that was made with the cloth jacket on it. Everything that was made with the cloth jacketed material, that was going to be tin. Now when I say tin, that was actually copper. What we're talking about is tin cladding. So it's going to be tin cladded copper is what we're going to refer to it as. Aluminum in residential wiring, that was used around the mid-60s to the mid-70s. If you don't know that already, you are going to want to write that down. So again, it's the mid-60s to the mid-70s. It's going to have plastic insulation, and single strand wiring really isn't allowed anymore. So the reason is there was something called aluminum creep. When it got warm, the aluminum wire would expand, and then when it cooled off, it would shrink. So the more it got used, the bigger it got and the smaller it got. That actually loosened up a lot of wires, or a lot of the screws that held the wires together. So because of which there were fires that happened in homes, and the fire investigations during their cause and origin have determined that it was because of the aluminum wiring that was in the house. They brought that to Underwriters Laboratory and a few other places where they did the testing, and then they started making changes into not allowing single-stranded aluminum or solid aluminum to be installed in any sort of houses. Now here in the state of Illinois, it should be known that we do have mandatory defects that we have to report to our clients. One of those, and there's only 5 of them, but one of those 5 is solid aluminum branch circuits. All right. So let's talk about that a little bit. The difference between solid and stranded is, to me it's kind of simple. It's if it's one solid piece of wire that's coming in there, or a single strand of wire that's coming in there, then it's a solid wire. If there's a whole bunch of strands that are in the wire and they're twisted together and then that's covered with the plastic insulation, that's stranded wire. All right. The difference between a feeder wire and a branch circuit, feeder wires are going to be coming from either the pole to the panel. They'll go from a panel to another panel. Those are feeder wires. Those, by definition, can actually be solid aluminum, but because of the flow of electricity, I don't think I've ever seen that much. We just can't get that much electrical flow that we're going to need in a house for those connections in a single strand. So solid aluminum, we talked about if it has the plastic insulation. Solid as opposed to stranded, and branch as opposed to feeder. You should be able to identify those. So when we talk about the flow of electricity on these things, there's another term I'd like you to be aware of called skin effect. Now, it's not a foolproof 100% deal, but it's still a good way to think about it. When we talk about water flowing in pipes, water flows inside the pipe. When we talk about electricity flowing on wires, they actually flow on the outside of the wire. So they flow on the skin. So knowing that term skin effect says that if I have one wire, then it's only the surface area of that wire where the electricity is going to flow. If I have a stranded wire, I have a whole bunch of surface areas, and that's going to allow electricity to flow easier. A nice analogy I like to use is the difference between melting ice. If I have 100 pounds of crushed ice, that's going to melt faster than 100 pounds of a solid block of ice. Because again, ice melts on the surface. So if there's more surface area with the crushed ice, then that's going to melt faster than the block of ice. Same thing. Electricity is going to flow easier on stranded wire than it is going to be flowing on solid wire, and that's because of the skin effect. So the speed of everything, in the conductors, the easiest flow of electricity, I think, is the tin. Right behind it, almost 100% of it, is going to be the copper. So they're going to be nose to nose, and tin would go just a little bit faster. And the last one is going to end up being aluminum. I kind of like to refer to that as the horse race, and that's going to end up being beetle bomb, and it coming in at last. So what does that mean? Some of what we have to do, I'm going to zoom in on that board a little bit, sorry. Okay. Some of what we do is check wire sizes and make sure we have the right size breakers that protect these things. So I know in the NEC they have a pretty extensive layout on what size wires, what size breakers, the distance that comes into play, the temperatures that come into play. But for the most part, for us, it's pretty standard. All right. So I like to encourage people to make a chart. And the first thing we should be doing is 3 different columns. The first column is going to be amps, and then we're going to put up here copper, and then aluminum. Okay. And now the amps are going to be pretty much our breaker sizes when we deal with this. So the most common breakers we're going to run into are 15, 20, 30. We're going to jump up to 50, 60, 100, and 200. So then if we draw a line coming across with these, we'll be able to write down what size gauge wire, or bigger, what size gauge wire should be on these breakers, all right? So if I had a 15 amp breaker, I should expect to see a 14 gauge wire if it was copper. I should also expect to see a 12 gauge wire if it was aluminum. Remember, we said electricity has a little less, it flows slower on the aluminum than what it does on the copper, so we're going to need a bigger wire, more surface area to allow that electricity to flow. 20 amps, 12, aluminum 10, copper 30 amps is going to be 10, and then this is going to be 8, 50 amps is going to be 8, and then 6. Hopefully you're seeing a little bit of a pattern here, as we go down into the wire size. 60 amps is 60, aluminum is going to be a 4, and 100 amps copper is a 4, but I like to put that off to the side. In the Chicagoland area, we're actually going to normally see a 3. So and it's not going to be in any tests or anything like that, but if you're going to operate in the Chicagoland area, I'd like you to know number 3 and Chicago. Number 2, aluminum. This is one of our more common feeder wires that we're going to see in residential electricity when we deal with the 100 amp services. And the last one, we don't follow this scale. We kind of flip it around a little bit. We go 2 and 4. And then what we're going to do is put a /0 after the end of that. And that /0, the 0 stands for aught. So it's, you know, if it's 1 0, it's 1 aught, 2 aught, 3 aught, 4 aught. Once we get bigger than 4 aught, then you start getting into MCM and just bigger electricity that we're not going to deal with. All right. So another term is cladding that's up there. All right. And cladding is basically when we put an object around another object. In other words, if I have vinyl cladded windows, that means I'm putting vinyl wrapped around a wood window. All right. So we actually run into stuff like tin clad copper, which I had up on the screen before. That means the actual wire itself is copper, but it's got a coating of tin on the outside. And since most of the electricity, if not all of the electricity, is going to flow on that tin, that's what we're going to be measuring as the wire and the wire gauges that we're going to be using. One that's kind of unusual is something called copper cladded aluminum. And I shouldn't say that it's unusual. It's a very common wire that we run into. And quite frankly, I don't think anybody's going to really recognize it unless they cut the end of the wire and peek up in there, or they're able to read the writing that's on the insulation itself. All right. But in this case, we have a aluminum wire that's cladded with copper as it comes in there. So I always like to ask a little bit of a test question whenever I'm doing these classes, and I know we really can't answer them right here, so I'm going to end up giving you the answer. If I had a 10, or let's say 100 feet wire, 2 of them, one of them was a solid copper wire, and we're going to say it's a 14 gauge solid copper wire, 100 feet long, and then right next to it I had another 100 foot long copper cladded aluminum wire, same size, they're both 14 gauge, they're both the same distance, they both have 120 volts pushing the electricity to them, they have the same amount of draw at the other end. So I always try to ask the question, which one is the electricity going to travel the fastest on? Is it going to be the copper cladded aluminum, or is it going to be the solid copper wire? And I usually get a mix of both, but if you take into account that skin effect, they're both going to be the same, or at least they should be the same when we come with it. This chart up here, I'd like to encourage you to write it down and memorize it. Every home inspection that we do, we're going to look at the breakers, we're going to match them up with the wire sizes, and make sure we have the right size breaker. You know, many times we're going to see things that are over fused. It's common. All right, so if I got a 14 gauge wire on a 20 amp breaker, it's not designed to carry that. Let's see if I can switch these lights a little bit. It's not designed to carry that as much. And when that happens, you know, that's considered overfusing. Now, in all reality, and I know I'm recording this, so I guess I can't deny it, I really don't see that as a big deal if I got a 14 gauge wire on a 20 amp circuit. It's wrong. I'm going to identify it as being wrong. We're going to document it. But, you know, fixing that is just put the right size breaker in there. And most of them aren't that expensive, so we're not going to get too much into it. But if I got a 14 gauge wire on a 40 or 50 amp breaker, now I'm really rolling the dice. That breaker is going to allow 50 amps to travel through something that's really only designed to carry 15 amps. And then I'm taking a big push on it. So every inspection that we do want to check and make sure that we do have the right size breakers for the right size wires. Now the other way around really doesn't matter. So if I had a 10 gauge wire on a 15 amp breaker, I don't care. I mean, I'm just limiting the flow that's going to go through there, but it's not like I'm creating any sort of hazards. I'm not making the wire the weak link, and that's what we want to avoid. We don't want the wire to end up being the weak link.